Hello and welcome to the penultimate study unit of this module. This is study unit 8 on binary trees. Now, binary trees is another classic in computer science, something that you will use often in future in other modules. So we are going to study binary trees rather intensively. We are not going to focus a lot on the programming part, but we are going to do a lot of logics and algorithms. Okay, exactly what are we going to do? We will try and implement a binary tree. How it is done? It's done with a linked list. Can you believe that you will do another linked list? We are going to search for an element. We are going to add the element. We are going to traverse the elements of a binary tree. And we are going to delete elements. So it is a data structure. It's a data structure that's almost always implemented with a linked list because it's much easier to do than trying to do it with an array. And luckily you guys understand everything about linked lists, so it should not be difficult. So in the first section we will talk about the first three, perhaps the first 4 items here, and then we will move on to the second part and third part for the rest. Okay, so first of all, what is a binary tree? A binary tree is a data structure. Yes, the idea is that you store data in a binary tree, but it is hierarchical. This means there's a hierarchy with the root, and the root has the left child and the right child, until you get to a leaf. But we will talk about these terminologies now. So you can store any object in a tree. It can be integers like these, or it can be letters. Later on we will do one with strings. It can be any object. And obviously our task will be to create a tree that is data independent, but you know how to do that now. Okay, later on your own time, you must come back to this slide. It's a little program that runs from the internet where you can search, insert and remove items in a tree. The tree is built for you, but then very interesting, you can do the traversals. The traversals in a tree, there are 3 ways, which all gives a different answer: in order, pre-order and post-order. So you can come and create a tree and with this little program and try over and over to say beforehand what will be the order. This is a wonderful tool while studying, and it has a hyperlink. So download the slides and just follow the hyperlink. Okay, let's move me around out of the way. I'll sit there on the earth at the bottom. So the root of the left subtree is called the root of the left subtree of a node is called the left child or the right child of the node. A node without children is called the leaf. So you can remember these terms. A special term in type of tree is a binary search tree. Our binary search tree, and this is the one we are using, has a property that for every node in the tree, the value of any node in its left tree is less than the value of the node and the value of any node in its right subtree. And that also that in the right subtree everything is greater than in the specific node. So this is rather important, but you will see it apply just now. Here's an example. If you have a number 60, everything on the left, this is the left subtree, is smaller than 60. Everything in the right subtree is larger than 60. And that works for every item. Yeah, if you look at another item, 55, another node, everything to the left is smaller than 55, everything to the right is larger than 55. Now can you see that it's a linked list? Every element, every node has an element, so that is called element, and then it has 2 pointers, not a next like in a typical linked list, but 2 pointers. It has a left and a right. Now you know by now that these are addresses, so if this is A00E, then that left's value is A00E. So this textbook does not write the addresses, but in there is an address stored, and that is the address where you can find this node. In there is an address stored, and that's the address where you can find this node. See how they declare it? You know this, I'm sure. If this was an exam question, and we asked you, how would you declare this class if we gave you the diagram? I'm sure you would have been able to do it, because there's an E, the generic, it has an element, the element is the data value, it has a left and a right, and look how it is defined, just like a linked list, as addresses of the same class, and the constructor receives a value of the type E and assigns that to the element. Cool. So you can talk about a node dot left, meaning the left and the left address, go to that address and find the object there. Node dot right means go to right, go to the address stored and go to that variable there. But we will do that over and over again. This is a very nice implementation of a linked list, something that makes very much sense. If you had to do this with an array, how would you order that array? Which order will the array take? Okay, so now we go for the first important and difficult item, but it's not as difficult because you understand linked lists and you are quite good with a linked list. I can just tell you that even if you do not understand linked lists, many students in the past started to understand linked lists after they understood the trees. So do not get negative, just carefully follow and perhaps we can solve your problem. The idea, when you search for an element, okay, you search for a specific element. The parameter would be the element you are trying to find, and we have a current pointer that's running through the tree, like we did always with PTR and the linked list. So let's first look at the logic. So we say if the current pointer, we first say create a current pointer. You know now why it's a tree node E, because that is the node of the tree, like on the previous tree. Create a new pointer and assign it to the tree's root. And we search while current is unequal to 0. If the tree is empty, root will be empty. Root is almost like head in a linked list. It tells you which is the root. It's with one difference. Head doesn't have a value item where root has a value item. Okay, so if it's equal to, you start with current equal to root now. While current is unequal to null, so this is a loop. Now look how easy it is. If the element is smaller than the current dot element, current should be current dot left. We'll go there in a moment. If the element is larger than the element, current is current dot right. And else, when will this else be executed? When the element is equal to current dot element. Then you have found the item you are looking for. So let's just go back on this slide and see if we can see that this is left and this is right. So current starts with root. current dot element is the 60, and root dot element is also that 60. So it says, is current dot element is that, let me just double check, current is, yes, is current dot element, is it equal to root dot element? No, obviously, if it is you return, but if it's smaller than, then current must move on to this node here. And to make current move down this line, you say current equals current dot left. Okay, let me just rewrite that so that you can see clearly. Current equals current dot left. Isn't that cool? It's like pointer is pointer dot next. But now it's not dot next, it is dot left. What do you do if you want to go to that side? So current is like a little window on this tree. And if you want to go to this side, you say current is current dot left. If you want to move your window down here, you say current is current dot right. Okay, so let me just see if I can do this a bit better. We can say current is a window here. This is current. And if I want to move current that side, if I want to move my window, so I want to remove this, I want to move my window, I say current equals current dot left. But I can also move my window this side, then that part is no longer there. And then to do that, I can say current equals current dot right. Where is this left and right? It's because this variable's name is left, this variable's name is right. So I take the left value, which is an address, and I copy it in current. You have to pause me and rewind if you do not understand this. But if you really do not understand, you have to draw this with addresses. EAB12, AB12, CCDE. I'm sucking these out of my phone. CCDE. And to say current is current dot right. But current dot right will be in this case CCDE, and then current will move down here. It is extremely important that you understand that current is like a window on this tree moving around and how you move it around. So if we go back to the searching algorithm, you start with current on root, and then you say while it's not null, meaning that there's still elements in the tree. Remember the leaves, let me just say that, the leaves have no values today. Very important. They don't tell you that ever. That all these values, those as well, have a value of null. And that is how that while loop will end. So while current is unequal to null, when I have not reached the end of the tree, if the element, the thing I'm looking for, is smaller than the current element, look through the window at the tree. If the tree is like this, current is like a window, and if the element is smaller than, I want to move to the left-hand side, then I move my window like that. If the element is larger than current dot element, I want that right to become my current. Okay, and else meaning this means if the which is left. The smaller than the larger one, the else is equal, then I have found it. Now, when will I reach this null value? I will, if it's not this one, if it's smaller than and it's not this one, it will be, let's say, smaller than, then current will become 0. No, it will get that value. And then the while loop will terminate and it will return false. We are going to take a break. But you cannot go to the next session until you clearly understand this. So I think first you have to re-look at this, look at the code, make sure you understand. Inserting an element in a linked list is very similar to searching for an element in a linked list. And there are nice examples here. But insert works with 2 pointers. Remember, in linked lists we sometimes work with a previous pointer and a pointer. In this case, we are going to use a current element and a parent, because we need to know the parent in the list. The parent is very similar to a previous element, to know how to insert an element. Okay, first have a look at the code. The textbook helps you a lot. This slide has a running example, but let's go through it. First of all, we are going to find a space for the element to enter it, and then we will add it at that position. So the first part is really quite like the search, except we have this parent run. So we have 2 windows on our list. So it starts with if the list is 0, or if the list is empty, if the tree is empty, you just create a new row, and then you are done. But if not, you start working. The current element, this is not Java, this is zero code. So it won't work just like this. We can ask you to do this in practicals, but it's outside the scope of the model at the moment. So the current window is the root. So I can draw my current there. If current is unequal to null, the same reason, because remember here there is null. If current is unequal to null, if element value is smaller than the value of the current element, if the element value, this is what is element? It's what I want to insert. To be inserted. To be inserted. Okay. If the element I want to insert is smaller than the current element, then I'm going to have to make my way here to the left side. The parent becomes the current, and the current is the left one. So this is now the parent, and this is the current. And I just continue with this process, else if it was larger, parent is current, current is right. And if I have, if it's equal to, you're not never allowed to insert a duplicate, then it's going to stop. Okay, so this will continue until current is null. So it will go until I find a leaf, and the parent is now the leaf, and the current is one level lower. Can you understand what I'm telling you? So every time I go left or right, current moves down, and parent sort of follows it. Now current will be 0 or null after I found sort of the place for the element, and parent will be the place I really want to insert it. So if element is smaller than the parent, create a new left node for this element, else create a new right node. Now, as I said, this book does something really nice. It tells you it will follow the code to insert 101. So let's follow that. Okay, so let's trace inserting 101 to this tree. So if the root is no, it's not. The current is the root. Now they use current with a little block, or you can draw a square if that helps you. While current is no, so current is not yet no. If element is smaller than the current element, so is 101 smaller than the 60? No, it's not. So I'm moving to that side. Is it larger? Yes. What's happening? Parent is now also positioning to that 60, but current moves one down. So parent is the previous node and current is there. Okay, and now I'm going back to my y. Is current no, not yet. Is 101 smaller than 100? No, it's not. So what will happen? I will go to the else, and now first parent will follow me, and current will move one down. Okay, now you should look carefully what's happening. Current is not no. Is 101 smaller than 107? Yes, it is. So parent becomes current, and current becomes no. Current is now no, and parent is this 107. And now back to the while stop, and now current is no. So now I'll continue here. So can you see that parent actually contains the value where the new element should be inserted? And now we should just decide whether we should go that way or that way. And if element is smaller than parent, which it is true, parent dot left. Now I'm going to replace this no here with what? With a new address. How do I get the address of that new tree node? Yes, I call new. I create a new tree node with that code, and it gives an address back which I copied in there. And that constructor should put a no for the left and the right. And there it is. We inserted an element in the linked list. Now you can do the same thing again, but not this step by step. We will go quicker through it with a 59. Let's play it with this and see if we can figure out how this 59 is inserted. But you have to actually see if you can do it the same way as the 101. So if we want to insert 51, we will, from the top, is the root no? No, it's not. Current is the root. So let's say current is there, while current equals unequal to no. If element value 59 is smaller than, yes it is, current will be here and parent will be there. Do you agree with me? So this part will be executed, and now I will go back to the while. Is current equal to no? No, it's not. If the element here is smaller than what I want to insert, I want to insert 59, so it's not. So I'm looking to this. If it's larger than, parent will come here, and current will go to the right side. Current dot right. Okay? And then I'm back at the 1. Is current no? No, current is not no. So current is not no. Okay. Is the element smaller than the value of current? Is 59 smaller than 57? No. So I will come here again, and I will see it's larger than. Then current will become no. Do you agree that current will now be no? And parent will be here at 57. And carefully remember current is current dot right and current dot right when current is here is equal to 0. So then I'm out of this loop. And then this if is an if element, parent is 57. If element is smaller than 57, element is 59, so it's not smaller. So then it will do the else. Parent right gets this new element. But we know better, because we know that this new creates this new object. It returns an address, and in there will be stored an address. Okay, once again, crucial to understand insertion into a binary tree. Would you be able to rewrite this as a practical for a program? Would you be able to translate this code into Java? The book didn't do it here, because with all the e's and the compare to's and everything, it's just too distracting. I'm sure you will be able to do it. For those of you that's looking for a bit of extra work, can go and try this, but it's outside the scope of the syllabus. Not because it's too difficult, because we only have 80 hours to give you in detail. Okay, let's take a break for now. Welcome back. Now we are doing tree traversals. Now you are used to walking through a linked list from start to finish, or through an array from start to finish, maybe from back to front, but that's not the case in linked lists. We are going to do 4 ways of going through a linked list. 4, and you have to be able to, for a given tree, stored as a linked list, 4 ways of 4 answers for the question. So the question is, indicate in which order the traversal will visit the nodes, if in order is used, or if pre-order is used, or if post-order is used, or in breadth first. Yes. Now you have to not only figure out how to do it, but you have to link how to do it to the name, so that in the exam you know exactly how to do this. And it's fun, we always ask this somewhere in tests and some exams and second opportunities, because it also marks really quickly. Now, there's a way to remember this. Now, I'm first going to tell you a little bit about there's how to remember this. There's always a current node and the left child and the right child. In order, pre-order and post-order tells you where the current node is. You want to write left, right. In order, you write left, current, right. So in between the left and the right sits the current one. Pre-order, what do you think? Yes, you tested current, left, right, because pre means before. So the current is before the left or the right. And post-order, can you guess? Yes, it's left, right, current. Okay, the idea is when you go left, keep on going left until there's nothing left to go left on. Then do the current element, which always is only 1. And then if there's a right side, go right as long as you can go right. But when you are going right, remember that you are actually moving the current element again, but I'll show you this. So this is kind of hard to do in order at first. So there's a lot of examples, and I also added a link to another set of examples. This is not something that's easy to teach. I have to warn you, I can show you over and over and over again, but you have to put glue on a check. Remember, in the first session, there's this little program, slide 2 or 3, where you can enter your own trees and there's a button for left, right, in order. So you can enter as many trees as you want, play with it until you get this right. Okay, so let's have a look at in order. Visit the left subtree of the current node first, recursively. This means keep on going. Then the current node itself, and finally the right subtree of the current node recursively. Now this recursively means that the tree replaces itself. You know what is a recursive. So it's like you move the entire tree, so the current node becomes where the right child was. We will do this again. But this recursively is a hint how to do it. But can you see left first, then current, then right? Post order. Post order is to visit post order, is to visit the, I think there is an error here. Oh, sorry, post order is first the left, then the right, then the current. Is first the left, then the right, and then the current node. So first the left, then the right, then the current. Can you see post order, left, right, current? The current is after. Okay. This can be very confusing. I'm always getting confused, so please bear with me. But I'm not going to start the video every time over because I want you to see that I'm confused. And what is it that confuses me? Because the same things will confuse you. And it takes time not to be confused. Okay? Pre-order will be, let's say, current, left, right. Visit first the current, then the left subtree recursively, and then the right subtree recursively. And breadth first is level by level, so you just go, that is your tree 1, 2, 3, 4, 5. Just follow the levels. That's the easiest. When you see that in the exam, you say, okay, now I have marks. And the others, you have to practice a lot because you will be, it's in the exam about, I don't want to lie to you, but it's about 6, 7 marks or even 8, which if you just understand this, you score those marks. So here's some examples. The blue is what we added, but it's now really part of the tree. In order is, say, left, current, right. But it's recursively. The moment we go left, that left really becomes our current. Okay. So we start at the first go left. But this left is now our current, so it's a recursively. So go left. Okay, so this left is the leftmost, so we start with 45. We start with 45. But there's no left to continue with. Now we do current. And our current is this 55 and now the right. But we do the right, but then the right becomes our current node. And it's again left, which there is nothing. Current we have done, and then first go down to 59. Then we have for the first iteration of the recursion now followed all the left. Now we do the current, and now we are going to do the right. So our tree is kind of this part becomes our tree now. And remember recursion, it creates a smaller version of the same problem. So that is now our problem. So it is as if we are doing left, current, right now on this tree. So left, and so the 60 was done before we started with a new tree. Left until you can go no further is 67, then current, and now we do right. But if we have if we go right, that right becomes our current, and we first go left again before we go up to that right. So every time our current moves really to the position where we are going. So therefore it is 100, 101, and then 107. So whenever you can go left, you go left. If you cannot go further left, you go back to the current, to the parent, before you go right again. Can you see why I say go back to that first slide, create your own trees, and try this over and over again? But some students just get it right immediately. I'm not one of those. I battle with it. Okay, but I always get it right at the end, so let's take another one. Post order. What is post order? Left, right, current. Okay, so we are going to go left, left, left until we can no longer. So that is why we start with 45, it's the left note. And now we go right until there's no more right. And that is why it's right. And now there's no more right. We have done left already. So now we end our current is that 57. Okay, so we have done right until we can't any longer, so that's why it's 55. Now, this is now our left from this note. This 60 is our current. So if we go, this is our left we are, so we will have to go right. But it is first now a left is our current note. That right note is our current note, and we first want to go left, so therefore we do this 67 because there's no longer anything, sorry, the 67, and now before we are going to current, we are going to right, but right is now our current note because we do this recursively, so we are first going to do this right, and then we are going to do left again, and now only are we going to that current of 100 and the current of 60. So we do the middle one last. There's a lot of videos on this on the internet. So if you really can't figure this out, go and find other videos explaining this as well. Okay, so let's see pre-order. Pre-order, you know, is current left. Pre-order is current left right. Okay, so obviously, can you see the I'm getting the hang of it? Can you? Current means go first current, then left. But then when we go left, left becomes our current, and we go for the 45 after that. Current left, and now we have done left, so we go right, and that right becomes our current, so we do it first. There's no left, so we do right. Okay, now we have done everything, and now this becomes our current because we did current left right, so this right part becomes our current, and so it's current. Therefore the 100 left, right, and then the 107 becomes our current, so it's again current left. That's right, so this one. That's easier. Now a few tricks to know. I think pre-order is kind of easy. In order has a trick. In order. So what was in order? The left, current, right. Always use the correct answer if in the sorted order. So can you see that left, current, right produces a sorted list? So if you see in order in the exam, you can simply write the numbers in the correct order. And pre-order is kind of easier than post-order. But you are going to play with this until you get it right. Let's have a look at bricks first. It's just per level 60, then 55, then 100, then 45, 57, 60, 67, 107, 50, 901. Then you see I take every level from left to right. We will do more examples. Let's do another example with names. It's kind of more difficult. It's going to be alphabetical now. So in order is, you know this, left, left, current, right. Okay, so I'm going to start with left until I can't get any more left, which is Adam. Then I'm going to go for current, which is Adam, and then I'm going to go right, which is Daniel. Okay, now to go up again, left. I've done left now. Now I'm going to do current, that's why I do George now. And now I'm going to do right. So I'm looking at the subtree. For this subtree, I'm going to go left first, so I can't go any further than Jonas, so I'm doing Jonas. And then left current, so I'm going to do Michael before I go right. But right, the moment I go right, it's kind of recursively, and that becomes my current. So I'm first going to go left again to Peter, and then to Tom. Do you also get the hang of this? Okay, let's see if we can do post order. Post order is left, right, current. So post order, left, right, current. I will go left until no further left can be done. Then I'm here with Adam. Then I'm first going to go right before I go up again. So I'm first going to do Daniel here. And now I'm going, this was my current at that right. So it's left, right, current. So now I'm going to do Adam. Okay, so now I'm moving back. So to George, my current. So I'm doing post order. I have done the left now, and I'm going to do the right. So Michael really becomes my current. I'm first going to do left. Yes, now I'm going to do right. But right means right becomes my top of the tree, so I'm going to do left first. So therefore Peter, left, right. There's no right, otherwise I would have done that right first. And now current Tom, now I've moved up in the tree to currents Michael and George. It's hard to think about this way of recursion. We are dividing the tree over and over and over again now. But in here, if I can get this to go there, if you click there, it you get a safety warning, but I think that file is safe, don't worry about that. Then I have a traversal of a binary tree for you from the internet, and this guy is quite good. Let me just see if I can get it better. This guy is quite good. It tells you traversals, it tells you there are two types, breadth first and depth first. Depth first are these three. Then it tells you in order, visiting how it works. Simply way is to use a recursion and call to visit the left, track to visit the node, then the right. You see here it gives you this recursive code. Perhaps that helps somebody to understand. And then it gives you an example which you can do without looking, and then you have the answer there. Then it does the same for post order. Post order left, right, root. That's a nice way of doing it. Root, left, right. And then it tells you breadth first, and then it gives you more exercises to do. So you can enter this also in that other slide. Okay, so if we go back there, so there's more information on tree traversals. You will need to make sure before the exam you can do these four. These are some of the easiest marks in the exam. You can do it or you can't do it. Remember, in order will give the sorted list. Please see this is a sorted list alphabetically. Breadth first is per level. And so you really only need to know post-order and pre-order. And just by remembering the formula, it helps you and to understand that it's recursively. Okay, we will do deletion next, but let's take a break. Now for the final part of our discussion of trees, we are going to delete an element of the tree. Now you should think about this. It's rather complicated to delete something from a tree because the tree structure should stay intact. So there's rules for deleting a specific element from the tree. And although this is not for the exam, you need to, it's good if you understand this. It enhances your understanding of trees. So if we go through this basic rule, we will see that it's very logical, it's very intuitive, but it's kind of hard to express it in words. To delete an element from a binary tree, you need to first locate the node that contains the element that you want to delete for sure, and also its parent. So remember, like the previous pointer. Let the current point to the node that contains the element in the binary tree, and the parent point to the parent of the current node. Now, it's like a linker. The current node may be a left child or a right child of the parent node. There are two cases to consider. So you know now in the tree, if we want to delete this one, current will be there and parent will be there. That's the only thing that's on the slide. But they say there's more to it than this. Case 1. The current node, the one I want to delete, the current and the parent, does not have a left child. No left child, as shown in figure 8. And then, if there's no left child, you simply connect the parent with the right child of the node. So the idea is that this right child, because this is now deleted, the current is deleted, that right child becomes the left of that parent. Okay, can you see this is what's happening? And it can be the right or the left subtree, depending if it's bigger or smaller than. Okay. Now, to do this, we are going to delete 10, for example. So 10, if we delete 10, that 10 does not have a left one, so we will simply take the 16 and connect it to the 20. Which side should it go, left or right? It will go to the left side because it is smaller than 20. Yeah, that's not too hard. Are you all still with me? This is when you, case 1, there's no left subtree. Okay, case 2. Case 2, let's do well now, I'm right at the bottom. The current node has a left child. Okay, the current node has a left child. Now we are searching for the rightmost point in that from that current node. Let rightmost, now we have a new pointer. Rightmost point to the node that contains the largest element in the left subtree. Rightmost, the largest element in the left subtree. That's not so hard. The largest element in the left subtree of the current node. And parent of rightmost. Point to the parent of the rightmost node. Note that the rightmost node cannot have any right children, otherwise it would not have been the rightmost node, but may have a left child. Replace the element value in the current node with the one in the rightmost node. Connect the parent of the rightmost node with the left child of the rightmost node. Oh, this sounds confusing, but if you look at the example, it becomes better. So the rightmost node is that one, and that's the parent. So the rightmost node we are going to connect, and we will see what happens with the parent now. Okay, so we want to delete the 20. The leftmost have children, so that's why we have to do this. So the rightmost one is the largest one in this tree. That we connect, the rightmost one, we connect, becomes the root, or we connect to whatever was connected here. So, and then the parent of it goes to the left-hand side. Can you see that one becomes the node, and then this child connects to the left side there. Another example will help you. The left side has children, so the rightmost one will connect to the top, and the parent will connect to its left side, the parent of the rightmost one. Okay, now a few other examples. If we just want to remove something with a leaf, we just remove it. If we remove something like Michael here, what's going to happen when we remove Michael? This left side does not have children, so the right side just connects to the left side. And our final idea is that you have, how long does it take to traverse the tree? It's order n because you only visit every item once. But to search, insert and delete is the height of the tree, how many levels it is. So much quicker than any other data structure. So trees are very quick to do. If you think about merge sort, we are creating actually a tree. Even if you think about quick sort, we are sort of creating a tree. So that's why we do trees with you. It's a data structure that's very quick to search. So what have we done? We first searched for something in the tree, then we added something in the tree, then we traversed the tree, and then we have these two cases for deletion of the tree. The deletion, the code is not for exam purposes, but it's kind of nice. It is for the class test. We can ask you in the class test how to delete something in a tree. So how we will give you a tree and say, delete this item, and then what's the new tree. Okay, so now we have completed study unit 8. Thanks. Hi everybody, this is an additional video on tree traversals. I want to show you a trick. Now, before I start, this wasn't my brilliance. It's one of our students, Lance Now, that gave me this shortcut trick to do this. And I want to share it with you. By the way, if you find tricks and think I do something it's very, very complex, which there's an easier way, please send me an email, then I will share it with you. This is beautiful, but you need to know a little bit to be able to do it. We always traverse a tree we can say from left to right. But in order, we traverse it left, current, right. In means in the middle. The current note we are going to do in the middle. Post order, we can say post, the current note is at the back, left, right, current. Pre-order, we can say first the current, then the left and the right. Now, let's take in order first and see if we can have an easy way to get to that sequence. Now, we are going to do, I think Lance said, the recursion helped it. So we write left, center, right, or left, current, right at the note. And then we say, let's first look at the left. Does this note has a left child? Yes. And then we tick the left so that we are done with it. And then we go to the left child. Why are we going? Because the L was at the beginning. And then we are right back where we started and say, left, current, right. Does this note have a left child? Yes. So we tick the L and say we are done with it. Left, current, right. You must always remember where you're coming from in this case, because we need to go back sometimes. So, okay, so now we are going to say, is there a left child? No, there's not. And now we continue to current. The moment we strike current, that is when we write down the number of the sequence, so 45. We continue to say, is there a right child now? No, there's not. If all three has been ticked, you go back from where you came from. And where did I come from? This note. So I have done the left already, that's why you strike it through. Now the current, since I'm doing current, I'm writing down the answer. And so current is done, and now I check right, left, yes, there's a right child. And the moment I do the right child, I go there, but I again write left, center, right. Do I have a left child here? No, strike through the left child. Do I have a current? Yes, 57, write it down. Do I have a right child? Yes, go right. The moment I'm right, I go left, current, right. Do I have a left child here? No. Do I have a current value? Of course I have a current. Do I have a right? No. So go back to where I came from. There, then I go up until I first find a position where I have not done left, current, right already. So left was done. Now I do current. Current means write it down. And now I'm going to go right. So I'm here, left, current, right. Okay, my first question, you guessed it, can I go left? Yes, I can. Left, current, right. Can I go left? No. Should I do now current? Yes, so I write down the number. Can I go right? No, there's no right, so go back. Okay, left, current, right, you've guessed it, write down the 100, and now I can go right. So left, current, right. Left, I can, 101, but a left, current, right, by doing 101, left wasn't there, current, write it down, no right, go back, write the current, 107, and there's no right to go, and then we are done. Isn't that beautiful? So simple. And can you already see that you can do the others as well? I think you should find Lance's telephone number and phone him, all of you, and say a big thank you. He won't think it's a good idea. Luckily you don't have his number. Okay, shall we do one more? I think, I don't want to bore you, and I'm sure you can do it. So pause me and quickly do, let's do something that's really different, pre-order, and see if you can do pre-order, and then check if you can do it. Okay, so here it comes, pre-order. So what am I going to write? current, left, right. Current always means write down the number. Okay, can I go left? Yes, now I have current, left, right. Okay, current means write down the number. Can I go left? Yes, current, left, right. 45, current, left there's no, right there's no. Now I go one level up, I can go right. Now I'm current, left, right. Can I do current? Of course, 57. I don't have a left, but I can go right. And now I'm current, left, right here. Can I do current? Always 59. Current is done. There's no left, there's no right. Go back there, everything exhausted. Go back there, everything exhausted. Go back there, everything exhausted. Except, of course, the right. So go right, current, left, right. Current is 100. And now I go left, current, left, right. And now I do 67. Current, and now I'm there. The current I've written down. Left, nowhere to go. Right, nowhere to go. Go up. Now I'm going right, current, left, right. Do the current first, 107. Now go left. Now I current, left, right. Current is 101. Left, nowhere to go. Right, nowhere to go. Go back. There's a right, nowhere to go. And I'm done. This is very, very simple and a great idea. You can now do post order on your own. Remember, on the main slides, there's a slide 2 or 3 where you can enter your own tree and you can practice this. There are buttons to compute the in-order, post-order and pre-order. This is going to be one of the easier questions for you in the exam. Good luck with that.